Before I start with the technical details here, I would like to start with a very short introduction of my person and with my background and my motivation to be here. So I've studied chemistry in Bielefeld in Germany and received my PhD in mechanical engineering at the University of Stuttgart in 2002. And I'm working now for over 25 years, nearly 25 years, for the Physikalisch-Technische Bundesanstalt. That's the National Meteorological Institute of Germany, which is comparable to NPL, National Physical Laboratory here in India, which is located mainly in Delhi. So we deal at PTB with the art of measurement. If you have to measure something, which is then based on the SI units, this is related to work in Germany, which is done at PTB. And I'm head of the Division 3 at PTB. So in this division, 200 people are working on the field of chemical physics and explosion protection. So beside other topics, we also have to consider energy efficiency here and safety issues if you deal with combustion. And so this is my motivation concerning the topic we are discussing here. But of course there's another motivation. So last week there was an interesting article in one of our newspapers about people from India working in Germany. So this number has increased from around 23,000 up to 130,000 in one decade. So maybe some other countries like US are closing their borders, but there are collaboration projects between India and Germany so that people from India can come to Germany and work there. And what was really surprising for me, that the average salary of the colleagues from India in Germany is higher than the average salary of the Germans. That means mainly people with high qualification come from India to work in Germany. That's one important topic. The other topic is we have 50,000 students from India at the German universities. And I have worked with students from India a lot, master's thesis, bachelor thesis, and so on. And the last example was a female student who has written a thesis about ammonia combustion in my lab, and now she is starting a PhD work at TU Braunschweig, not in my institute, but in an institute at TU Braunschweig, again dealing with the usage of ammonia as an energy carrier. So there is a strong interest to have better cooperation with Indian institute like IIT Guwahati, for example. And to close this, my first PhD student I hired 2002 came from IIT Chennai, and so he received his PhD in Germany, also at University of Stuttgart, and now he's a professor at the Indian Institute of Space Science and Technology in Kerala. And two of my colleagues have visited him last week, so we have a project on ammonia combustion again. And I hope in the future we may have a collaboration with IIT Guwahati and a research project together. So this is my main motivation. But another topic is, of course, talk about fundamentals of combustions mainly related to the change of our energy infrastructure away from fossil fuel towards renewable energy carriers, hydrogen, ammonia, and so on. And when we have discussed, Professor Sahu and I, when we have discussed about the topic of this program, of course we have to deal with the fundamentals, like in the first lecture, fundamentals of thermodynamics. Now we have to talk about fundamentals of the combustion kinetics. But we have to be, it has to be clear that we just discuss it very briefly. Of course, there are special lectures for each of the different topics. So we have numerical combustion, we have combustion kinetics, and so on. So the main focus at the end is renewable energy carriers and safety issues using these. So first question is, are there any chemists here? Has anyone a strong background in chemistry? Or mainly mechanical engineers? Yeah. So when in Germany, mechanical engineers, when they deal with combustion engines, they are looking at the efficiency. So horsepower, that's the important part. And the combustion process is, okay, it takes place, but it's not so of interest. But when you look at the combustion process, of course, it's chemistry. This is pure chemistry. You have fossil fuel, like gasoline. At the end, you have carbon dioxide and water, and unfortunately, soot and NOx formation and so on. This is pure chemistry, and you just use the energy which is stored in the chemical molecules to produce heat and power. That's it. So the engineer is interested in transferring the energy, and the chemist is maybe interested in the combustion kinetics, but of course we need both here to understand this process in detail. I have given here some literature, and when we look at online courses, and so one of the ideas of this giant course is also to have online lectures available. Of course, there are really good online courses. One example is here the Combustion Summer School at Princeton University. So these courses you can also find at YouTube, and really good experts talk there about similar topics. So motivation concerning combustion chemistry. You all may know the Bunsen burner, where you use normally natural gas, methane, and this is burned with air. And you know that you have a screw at the bottom of this Bunsen burner, and the idea of this screw is that you can change the concept of the burner. It's quite simple. If it's closed, you have a non-premix system, you have a flow of methane, you have a flow of air, and the combustion takes mainly place at the boundary between these two flows. You have a non-premixed or classical diffusion flame. It's not so efficient, and this you can see here. It's a quite yellow flame because we form a lot of soot molecules. So the flame temperature is not so high, and this yellow flame stands for soot molecules which burns later on. And then if you open the screw and mix the methane flow with some air, you change your flame behavior towards a premix flame. We have a very, very efficient, very located flame region here. So from this unstable, flickering yellow flame, you change it to this blue flame, and maybe if you have ever used a Bunsen burner, you can hear it also, that the efficiency becomes better when you go to this Bunsen burner flame or this premix flame. And what is also important, the color is changing. Here we have more soot, giving the yellow color, and here we have mainly UV blue radiation from CH radicals and so on. So it's the same mixture we are burning, methane with air, but it's totally different. And this is, of course, depending on the change of flow configuration, which then has a big impact on the chemistry which takes place at the end. And another motivation, this is then my background, safety. So here we see a BLEVE, boiling liquid expanding vapor cloud explosion. And a tanker filled with LPG was in a fire and then exploded. And you can see here some houses. So the flame ball we see here has maybe a height of several hundred meters. And what is important, such a big flame, that such an accident always starts with a small ignition event. So, and to understand ignition, of course, you have to consider then again combustion chemistry. Otherwise, you cannot describe all the details here. So these two examples may have shown that combustion is a complex interaction of physical processes and chemical processes. So we have fluid dynamics, heat and mass transfer, thermodynamics, and chemical kinetics. And to describe combustion properly, we have to consider different properties, so stoichiometry, heat of formation, heat of reaction, just some few examples. Then we have different flame types. So we have this classical premixed flame. So here we ignite. So we ignite and premixed here propane air mixture in the center of a vessel, and you see at the beginning a classical laminar flame which is expanding, and then at the end you see this wrinkling and you have a turbulent flame. So when we consider premix flames, we also have to consider deflagration or detonation. So either subsonic combustion, mainly to diffusion, molecular transport and thermal conductivity, or detonation, so supersonic combustion propagating through shock, adiabatic compression. We also have non-premix flames, maybe in classical examples here the candle flame we see. And of course we can have, especially in technical applications, something in between, so partial premix flames, triple flames, and so on. So to explain this detonation, again, so here we see an colored Schlieren image of such a detonation. So here we have a shock wave in this area, and this shock wave compresses our unburned gas mixture, and due to this compression, of course, we have an increase in temperature, and if everything is working properly, this increase is strong enough to ignite the mixture, and then at the end the flame can propagate with a sound of velocity um, through this gas mixture, and so the flame propagation is much faster in a detonation, and which is also very critical for safety issues. When we consider a normal deflagration, we have a pressure rise of 10 bar, or 10 times the initial pressure. The detonation, we have a pressure rise up to 100 times the initial pressure. And when we then look at this DDT, deflagration, detonation, transition, there we can reach much higher pressure, so 150 bar, 200 bar, which then of course is difficult to handle if you have this in a pipe or somewhere else. So to show you some examples, hopefully these videos are working. So here we have a stoichiometric methane air mixture, and so it's ignited here at the end, and you see the flame is propagating through this tube, and at the end you can see the interaction of the flame with the gas flow, so this oscillating flame we see. We can also have a look at a detonation here. So the ignition starts somewhere here at the left, and then it accelerates here. The detonation takes place, and it continues as in a typical detonation. As I've said, we have much higher pressures here, and here I show you some examples with a pipe made of plexiglass. This has a burst pressure of 140 bar. So it's quite solid, but here we use propane air mixtures. So the ignition again starts here, the flame propagation. The flame accelerates, and now there's the DDT, so the transition to the detonation. And at this specific point, the pressure was so high, you can see it here. The pipe was destroyed, and because it could not withstand the explosion pressure. Okay, so here we see the images of this video. So the flame accelerates, and at the end it has a velocity of 2000 meters per second. So coming back to the fundamentals. So the chemical reaction we have to consider, for example, methane plus oxygen in air gives carbon dioxide and water. So quite easy. And if we look at the fundamentals, okay, the atoms are conserved. So we have one C here, and we have one C on the other hand, and so on. So we always find the hydrogen atoms and oxygen atoms and so on both sides. Of course, the number of molecules are not conserved. So here methane is changing towards carbon dioxide and so on. Then we have to consider stoichiometry. So we have propane, which burns then with air. So in this case here, 5 quantities of oxygen plus nitrogen gives then carbon dioxide and water, and of course nitrogen plus heat. So the ratio here is then of course important concerning the stoichiometry, and if the air-fuel ratio is correct, we can have a fuel equivalence ratio of 1. So we have stoichiometric combustion. So all combustibles and air or oxygen molecules are then consumed. But of course, if we have not enough propane in this example, we have a fuel equivalence ratio smaller than 1. We have lean mixture, lean combustion. And on the other hand, if its phi is larger than 1, we have rich mixture, rich combustion. In Germany or Europe, we often use also the air equivalence ratio, which is just 1/phi. So when we consider combustion kinetics, we have to consider chemical species, the type of reactions, elementary reaction steps. We have to develop mechanisms, mechanism, detailed reaction models. We have to consider ignition and peroxychemistry. And at the end, also, we will discuss reactors and diagnostics to investigate chemistry on the molecular level. So this is very, very important, of course, if you want to consider efficiency. So for example, peroxychemistry is very important, especially at low temperatures. So you can have unwanted ignition phenomena and so on. So we will discuss the fundamentals of elementary reactions, and we will discuss experimental methods, maybe mainly in another part of this lecture. So chemistry. So of course we have our atoms, hydrogen, oxygen, carbon, nitrogen here. We have our molecules, methane, oxygen, carbon dioxide, water. And the reactions we consider are taking place using radicals. So we have the OH radical, the methyl radical, L02. So we have different levels here. And at the end, if we consider, for example, pollutants, we also have a lot of aromatics. So classical benzol, toluol here, or benzene, toluene. And these form higher hydrocarbons, so polycyclic aromatic hydrocarbons, which then at the end can form soot. And here, for example, then we have very specific molecules, propagyl radical, propene-alene isomerization, which is important for soot formation. So if we have to consider this, we have to go very deep into the chemistry to understand this properly. And so the molecular structure of our combustibles is of course important concerning the combustion properties we have. So when we look here at these different molecules, so we have cyclic hydrocarbons. So benzene, when it burns, forms a lot of soot, and THF has nearly no soot, and here this explosive at the end, RDX, has no CC bonds, and therefore it does not form any soot at all. And on the other hand, we see this knock tendency, so unwanted explosions, pre-ignition in our combustion engines. So we have these molecules which with a complex structure which is very stable. So the tendency of knocking is very low here, and then we have this heptane here, which easily tend to knock. So when we then look at the details, okay, we have seen the one equation already. CH4 plus O2 gives carbon dioxide and water. This is not the level where combustion takes place. So that's a global reaction. So we have our fuel plus an oxidizer giving the products. But the real life happens on this level, on the level of the elementary reactions. So we have methane, which at the end gives carbon dioxide. But it depends, for example, on the stoichiometry. If you have a fuel-rich mixture, then it takes more in this way, reaction pathway. Or we have a lean mixture, it can take more this way. So we have a lot of elementary reactions here, and we have a lot of intermediate species to consider. So for methane, classical reaction mechanism has around 50 species and 150, 200 elementary reactions to describe this system properly. And larger hydrocarbons can have thousands of elementary reactions and hundreds of species which we have to consider. So, which is then quite large. And then, of course, if you consider, for example, numerical simulations, very expensive, because for each species, normally we have to solve one differential equation. So this overall global reaction here, H2 plus O2 gives water, can also be divided into a lot of elementary reactions. So we have an initiation of our reaction. So here that's the formation of hydrogen radicals. Then we have a chain propagation. So one molecule reacts with a radical and gives another molecule and another radical. H2 plus OH gives water and H, for example. We can have a chain branching. So H plus O2 gives H plus OH. So one radical on the left-hand side and two radicals on the right-hand side, which accelerates our combustion process. But we also can have termination. So H plus O2 gives HO2, and so on. So we have a lot of different reactions to consider, and finally we also have to consider wall reactions depending on our system. So the rate of an elementary reaction is determined by the concentrations and the rate coefficients. And the rate coefficient K depends on temperature mainly, but also it can depend on the pressure. So the example here, so the elementary reaction is H plus O2 giving OH plus O. So the temporal change of the concentration of the hydrogen atom is equal to K times concentration of hydrogen times concentration of O2, and so minus dH over dt is equal DOH over dt, and the the formation of O2 of O has the same rate than the formation of OH. And these are normally following in the classical Arrhenius form, so K is equal in pre-exponential factor times temperature times the exponential factor where we have the activation energy EA over gas constant and temperature. And often this temperature here, or this temperature coefficient, has also a temperature exponent. So it's not always equal 1 or 0, it depends. So, and the focus of this lecture part is here how we can determine experimentally and theoretically the elementary reaction at the end to form or to yield a proper reaction mechanism. So it's very important is to consider the order of reactions. So if it's, for example, of the order 1, first order, so then we have this logarithmic equation. So the concentration of A at time t over the concentration of A at the beginning, the logarithmic of this ratio is minus K times t minus t0. So we have a linear relation here. So a linear decay when we look at this logarithmic term here. And for second order, it looks different, of course. So we get different results depending on the order of our equation we have to consider. So we have a lot of different type of reactions. So isomerization reactions, parallel reactions, consequent reactions, chain reactions. And this has to be considered if we want to develop a proper reaction mechanism. So one example here, isomerization reaction. So that means the molecule has the same chemical composition, but it changes its structure here, butane and isobutane. So this is very important. So because the different molecules we here then consider, then of course reacts very different in further subsequent reactions. So we have parallel reactions. So A can either form the molecule B or the molecule C here in this example. So the temporal change of concentration of A is equal K1, so reaction 1, A to B, times concentration A plus K2 times concentration A, and the overall reaction rate is K1 plus K2. So we see it here. So we have this exponential decay of A, and then the formation of B and C depending on the values of K1 and K2. And we can use then this simple equation system to calculate the consumption of A as a function of time and the formation of B and C as a function of time. So it's quite simple here to have a look at this system. We can have reversible and or opposed reactions, which then of course it looks much more complex, but these are just two elementary reactions. For example, here in this example, the forward and the backward reaction we have to consider. We can have consequent reactions, so A gives B gives C. So, and again, here we can use a quite simple equation system to calculate the temporal evolution of all the species here. This is very important because in some cases the consequent consequent reaction B to C is much faster than A to B, and then often we can neglect this slower reaction or the faster reaction, because only the slower reaction is dependent on important here. So chain reactions can be observed in a lot of applications, so populations of bacteria, nuclear reactors, and of course chemical reactions. And the idea is, so we have an temporal change of a quantity, and this depends on the reaction rate and the amount of the quantity, and it can either be smaller one, larger, smaller zero, larger zero, or equal zero. And then of course either we have a decay, if it's smaller zero we have a growth, or it's stable. And we have several types of chain reactions, which I already have explained on some of the previous slides. So temperature and pressure dependence of our reaction rate. So we have this Arrhenius type, so this Arrhenius equation, K is equal pre-exponential factor and then activation energy over gas constant times temperature. And when we look, for example, at this decomposition of H2O2, we see the temperature, the reaction rate depends more or less linear here from 1 over T. So classical Arrhenius equation. We also can have a pressure dependency. So the reaction rate changes with pressure. We have more or less two different reaction rates to consider. One is here the infinity value at high pressures, where we have more or less constant value, and at lower pressure this K changes with a specific function depending on our reaction. So we have discussed a lot of terms now. We have discussed elementary reactions and the dependency of these elementary reactions. So the question is now, how can we use this? Why we need it? And so the idea is, of course, to couple all these differential equations to form a chemical mechanism to describe the combustion of hydrogen or of propane or of diesel or jet A or whatever, considering as many chemical steps necessary to describe our system properly, but of course to describe it in a way as efficient as possible. So neglect reactions which are not of importance and focus on the reactions which are really, really important. So we have to combine all the elementary reactions we have to describe our combustion systems. Here in this example we have 5 different reactions, and at the end we have to couple all the rates together when we want to look at the formation of all the species. So H atom we have to consider here, 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 and here, and here. So it's either used or it's formed in the reactions we have. So we have to know the reaction rate of all the reactions we have to consider here, and we have to know the concentrations of all the molecules and atoms we consider here. So at the end, the temporal change of the concentration of H in this example depends on all 5 reactions here, and we have to know all these data. So we have the same here now as an classical equation. So the we have to consider elementary reactions. The number is here R, and we have to consider S species. So at the end we will sum up over all the equations the change of the amount or of any molecule. So at the end we yield a description like this one here. So the temporal change of the concentration of each molecule is then just described as the sum of all the reactions this molecule is involved. So this is we have to consider. So this is the global expression, and here this is the example for this specific case. So of course if you have hundreds of reactions, then you have to of course consider much more details here. So a reaction mechanism is a coupled set of differential equations for all species involved in the reaction steps. So it is a large database. We have to know the thermodynamic properties, so heat capacity, enthalpy, and entropy mainly of all the species, to calculate the reaction rates here. And then we have to of course to know the reaction rate parameters, so the pre-exponential factor, the exponential term here, and the activation energy. And I've said it before, the size of the mechanism we use strongly depends on the molecules we consider. So H2 can have a quite small mechanism. In this example here, 7 species and 25 elementary reactions. And in case of this cetane mechanism as a diesel surrogate, we have 1,200 species and 7,000 elementary reactions to consider. So how do we develop such a mechanism? So we can use theoretical concepts. So there are existing reaction mechanism generators. So where we more or less, or simply speaking, we say, okay, we want to describe the combustion, for example, of methane with oxygen. And this mechanism generator then sums up all possible molecules which may be involved in this reaction, and all possible reactions which can take place. So it gives you hundreds of species, thousands of reactions, and the idea is then, of course, therefore it's a generator to filter this big list we have and to get a smaller, proper reaction mechanism at the end. We can use the so-called master equation to describe our system, a more classical concept, but based on quantum mechanical calculations. This is maybe the future concept. So we describe the different states of our system in all details using quantum theoretical calculations and get then the reaction rates of all the reactions we have to consider. So in the future, with enough computer power, maybe no one is bothering about any mechanism reduction and so on, because then the computers are fast enough to handle even very big mechanisms. Then, of course, the traditional setup is CH4 plus O2 gives CO2 plus H2O. So what are the reactions I assume? So what radical reactions I may have to consider? So someone can write down this by hand. So an approach like this RMG, but the traditional approach. Or we can, of course, then look into the literature and then see for different sub-mechanisms, maybe different reactions. So for linear combustion, we may find different reaction rates compared to rich combustions, and so on. And finally, of course, we need experiments to look into at least some of our reactions into detail to determine the reaction rates. So here an example, the thermal NOx formation, or so-called Seldovik mechanism. N2 plus O gives NO, so nitrogen monoxide, and we also have then N plus O2 again yielding NO. So we get here three differential equations to describe the formation of NO and the decay of N, decay and formation of N, and the usage of O2 here. So this is a very, very simple sub-mechanism then to describe the NOx formation in combustion processes. Another example is the typical beta decomposition of hydrocarbons. So here we have our propane molecule, which is attacked by an OH radical. This takes one H atom to form water. And then, of course, we have this radical here, this N-propyl radical, which then normally decomposes here at the beta position. And we get ethene, C2H4, which then may form acetylene at the end, C2H2, a classical soot precursor. And we have this methyl radical, which then gives formaldehyde as a stable molecule on this side. can be very complex. So we have here, for example, the reaction of methyl radical plus O2, which gives this intermediate molecule here, and this intermediate molecule can either decompose in this way or this way, or form another form of this molecule here. And you see we have different energy levels when we look at this reaction coordinate. And of course all reactions can take place, and the science is here now to consider which are important for my specific combustion process. Is only this way here to formaldehyde plus OH of importance, or do I have to consider also the other reactions I'm describing here?